Okay, perfect. So let's get started with the lab session. Before we start the hands-on lab, everyone on their own, I will first give a brief introduction into Cilium, Tetragon, Hubble, and so on. My name is Schmid. I'm a solution architect, part of the Isovalent customer success team, which is our post-sale team, which is also covering 24/7 support, for example. So we are Isovalent now for a bit over a year, part of Cisco, but our journey continues to be the same. We are, we are still the core maintainer of those three projects to see over there. On the left-hand side, we have Cilium, Hubble, and Tetragon. All of them are CNCF projects under the Apache 2 license, and they all are highly based on eBPF, which stands for Extended Berkeley Packet Filter, which is a Linux kernel technology. So on the left-hand side, those are all open source projects. We are the creator and the core maintainer of them. And we also have enterprise editions for Cilium, which also includes Hubble and Tetragon, with, for example, a 24/7 support. So let's first talk a bit about the technology basics to understand what we are doing afterwards in the hands-on lab. First, eBPF, which is the foundation for all those other mentioned technologies. So with eBPF, you can extend the kernel functionality within a few seconds or minutes, which would otherwise take months, if not years, to get new functionality into the kernel, is now basically a matter of writing a few C code lines, compiling it, loading it in the kernel, and your kernel is extended. Basically, what JavaScript is to the browser is eBPF to the kernel. With eBPF, you can attach so-called BPF procs to specific hook points within the kernel. So in the kernel, those hook points are called K-probes, so kernel probes, or also trace points, for example. And it allows you to, for example, being executed as a BPF program whenever a specific syscall is called, or just any kind of Linux function. It could be, for example, a process trying to read some files from the disks, or a process initiating, here in this case, a TCP IP connection to, for example, an outgoing target. So that's also what's highly used by Cilium. And here we have the Cilium agent that actually compiles or creates the BPF program, loads them into the kernel. Before they are actually executed in the kernel, we need to ensure that they are actually safe to run within the kernel, because we do not want, basically, to mess around with our kernel stability and reliability. And therefore, we have the so-called eBPF verifier that verifies, for example, that the program, like the eBPF program that is about to be loaded into the kernel, does not have endless loops, for example. And once the BPF program is loaded, it can basically be attached to any configurable hook points. Here in this example, for network communication. And then, once in the kernel, we need a second construct, which is here also listed and shown, which is the BPF maps. And using the BPF maps, we have an option to either kernel internal between the BPF program to exchange data, or also to exchange data to, for example, a user space agent. What here in this case, for example, could be Cilium agent. For example, also Hubble that actually reads the data from the BPF maps, for example, to create flows for pod-to-pod communication within a Kubernetes cluster. So what is Cilium? Cilium is essentially a CNI plugin that implements networking for your Kubernetes cluster, which also includes cloud distributions like EKS and the other major ones. In its core, it provides networking functionalities for pod-to-pod communication, but also if a pod tries to connect to the outside world, or if an external user or external system is trying to reach some workloads running on the cluster. It comes with advanced features, for example, like transparent encryption using IPsec or WireGuard. So all of the TCP or UDP connections within the cluster are directly encrypted out of the box without relying on any workload-specific encryption methods. And other features are, for example, like BGP connections to some external systems or external BGP peers to announce specific IPs, for example, the load balance service IPs. It could also be something like Cilium cluster mesh, where you mesh multiple clusters together, so it's easier for the workloads to connect to other workloads on other clusters, on the remote clusters. And so then there are basically plenty or close to endless different functionalities. And on top of that, we have the Hubble layer, which is kind of the Cilium's observability layer, which provides you visibility over the connections that are actually happening to from your cluster and also within your cluster. In the end, you can expose these or those flows as metrics, or you could write them to a file and export them to a SIEM of your choice, like Splunk, Elasticsearch, or whatever you're running there. Like on top of that, we have the so-called Cilium Service Mesh, and there that's pretty comfortable feature from Cilium that comes out of the box. You just need to opt in and then you're ready to go. For example, if you need some kind of ingress controller or even like its successor, like Gateway API, it's just few flags within the Helm values, for example, when you deploy Cilium, and you're ready to go. You already have an ingress controller or Gateway API instance running within your cluster. So Cilium also has a pretty powerful networking policy feature set, which allows you to exactly limit like what application, for example, is able to communicate with which other application. And this can be like either on layer 3, layer 4, so on IP and TCP layer, or could also be like on layer 7, for example, for DNS or HTTP or some other specific protocols like Kafka, for example. Like as we all may know, like the whole ecosystem or like the whole pod situation within a cluster is very dynamic, which means like a pod can run for a few seconds. It can be terminated on one node, rescheduled on another node. Whenever this happens, like a pod gets a new IP address, so we can't apply traditional like networking filtering approaches where we would do the filtering, for example, based on access lists, for example, based on source IP addresses. And with that, Cilium like added an abstraction layer through identities, so-called Cilium identities, which basically represents all unique workloads within the cluster with the labels. So basically, whenever there's a unique label set for a workload, it considers it as a separate identity. And you can then apply your policies, for example, the job frontend.yaml network policies or the jobs policy YAML and so on the cluster, and Cilium will take care about the policy enforcement. So here, for example, we could configure that pods with those two labels, role frontend and app jobs, is able to communicate to the backend pods, which are labeled with role backend and app jobs on a specific port, for example. So you could filter on layer 3, so basically IP level. You could filter on layer 4, port level, or you could also do filtering here in this example based on HTTP. For example, for HTTP headers or HTTP endpoints or HTTP verbs. So it has like a huge feature set regarding the matching capabilities. For example, we can match on community-specific information. We can match on DNS names, so FQDN, or also like even regex-based patterns. So for example, if you want to match for star.yourcompanydomain.com, that's also possible. You can do CIDR-based matching, for example, for specific IP range, IPv4 and IPv6, both is supported. And then we also have integrations into cloud providers. For example, for AWS EKS, you can kind of connect it to like the security groups, and you can then use the security groups from the VPC to actually implement networking restrictions, like in form of network policies, using Cilium on your cluster. Now, what is Hubble? Hubble is essentially the observability tooling built on top of Cilium. So it's highly coupled to Cilium, and it provides you visibility for what's happening within your cluster. So you see every single connector connection that is happening from one port to the other port, and so on. It provides these details, or like can provide those details as metrics, so you can export them to OpenTelemetry, to Prometheus, whatever you're using there. It doesn't matter. Or you could use Hubble internal tooling, for example, the Hubble UI, to visualize your network connections and your services within the cluster. Last but not least, it also offers the so-called Hubble CLI, which provides you a pretty neat and powerful CLI similar to TCP dump or, for example, T-Shark, to see what's actually happening on your cluster. You also have a variety of different filters available. For example, you could filter for namespaces, port names, port labels, like TCP flags, and so on. Basically, it provides flows that are kind of an aggregation of different data. So first we have the flow metadata from like the actual networking stack. So here we have stuff like Ethernet headers, IP headers, TCP flags, and so on. And this information is then aggregated or enriched with, for example, the metadata from Kubernetes. So we can then correlate those like Linux networking kernel data with networking, with Kubernetes metadata. So we see like from which specific port this connection is coming from. In addition, we enrich those flows with, for example, a policy verdict, where you would see, for example, policy drops or like drops of network flows based on your implemented Cilium network policy rule set. So it helps you directly to troubleshoot in case you apply a new network policy, which is might or perhaps still has some bugs in it or like allows the wrong connections. You would see that by having a view at the Hubble flows. Like in addition, last but not least, we also have the DNS-based data, and there, if enabled, it's opt-in. You can, for example, replace like actual external public IP addresses from websites, for example, Google 8888, whatever, with the domain name in case like you enable the domain visibility, because then Cilium also intercepts the DNS requests and replies that are happening on your cluster, and it therefore learns to which remote endpoints the clients like the workloads are connecting to. Here's an example of the Hubble UI service map. That's how the Hubble UI looks like. Here in the middle, you have the service map, basically showing you which microservices are communicating to which other microservices. At the bottom, you have a nice table view where you see the signal flows. You can click on them and have more details. For example, if you enable layer 7 visibility, you even see stuff like HTTP headers, HTTP methods, HTTP return code, and so on. If you're more kind of like the CLI guy, then you can also use the Hubble CLI. For example, here, Hubble Observe, filtered for a specific label, pod label, class equals X-Wing. And in this example, we see how this pod in the default namespace, the pod is called X-Wing, is doing DNS lookup through kube system hosted core DNS. We see the reply coming back. And afterwards, we see a connection coming from X-Wing going to www.disney.com. We see the TCP three-way handshake and so on. And in the end, for example, let's assume it does an additional network connection from X-Wing to, for example, DevStar. There it's denied because there's a policy which blocks it. So we actually see it's denied because we have a policy in place. Last but not least, let's also briefly talk about Tetragon, which is our runtime observability and enforcement tool. It's also highly based on eBPF, and it can run like complementary to Cilium on a Kubernetes cluster, but it can also run on any Linux machines. So it can run on a Kubernetes cluster where you do not run Cilium at all, it doesn't matter, or it could run on standalone Linux machines. Like the basic prerequisite is just you need to have eBPF, what's currently only available on Linux. But yeah, like folks like from Microsoft and also Cisco involved, we are working on it to also bring it to Windows, but that's another topic. Like for now, it can run on any Linux systems. It provides you visibility regarding your runtime. So you see, for example, like when a process is executing a specific syscall, at which time you see, for example, when a process is initiating a TCP connection to any kind of remote system, you see file reads, writes, basically close to whatever you like. It's up to you and your imagination to kind of configure the policies and create events for those use cases. So why Tetragon? There are many reasons, but let's stay with those three. First of all, Tetragon is Kubernetes aware, which again provides huge benefit, like not only seeing the specific syscalls happening on your system, but you also get context with your, for example, with regard to your Kubernetes workload. So you see like from which pod, from which namespace this syscall was triggered, for example. So here we have a syscall. So a binary was executed, and right away we see the pod, which was the pod, in which namespace, from which container, from which image, and so on. And we also see like Linux capabilities here in the middle. We see Linux capabilities, the permitted ones and the effective ones of the processes. And last but not least, we see the actual Linux namespaces for the different types, for example, networking namespace, ID, and so on. So overall, this allows us to build something like this. We have a namespace where we have a crawler pod in it. It's started through the container runtime. So we see the full process ancestry tree. We see the process tree within the pod. And here, for example, we see the PID1 of the container is a Node.js application, a server.js. And here we also see that it tries to connect, or it actually connects to API trader.com, to some internal cluster, even cluster internal Elasticsearch and so on. And then suddenly, like 5 minutes after like the PID1 is started, we see some other strange looking processes coming up. Netcat tries to connect to somewhere external. We see the domain name, like notaryvershell.com, for example. And we could then see additional network connections, for example, to dump or get some data from the internal Elasticsearch. And we could also see potential data exfiltration, where we see uploads to like any kind of external S3 bucket, whatever. Yes, that's a question.
Is this a UI output or you just designed it, right?
Yes. So with like previously, there was a very, very similar UI available in the Hubble Enterprise UI. But now we are in the process to replace that with a Splunk app. Like as of now, that's our plan to build a Splunk app. Like kind of obviously, like we are part of Cisco, Splunk is part of Cisco. But theoretically, like the data is there. So basically, whoever has the data could build something similar. Then another reason why somebody might want to use Tetragon is there's a pretty comprehensive like open source observability policy library. We have policies in there from like our engineers, our Tetragon engineers, our like marketing engineers, but also there are plenty of policies from the community itself. So there you find policies like for basically getting an event whenever there's a binary execution happening /temp, or if there's a privilege escalation or somebody's executing sudo, and so on. And last but not least, as Tetragon is based on eBPF, and we try to do as much as possible within eBPF, we have a very low overhead on your system regarding resource usage. So here, for this benchmark, we built a Linux kernel version 6.1. something, which resulted in a total event number of 1.5 million events, and it took about 550 seconds. Now, if you do the same baseline or like the same compilation of the Linux kernel with Tetragon in the background, we see only an increase of about 1%, 1.6%. And if you also enable like the JSON-based event generation, we see an overhead of up to 2%, 2.5% time-wise. Now, if you compare that to the CPU, we see that it's even a bit lower. For example, with Tetragon here, the yellow bar in the middle, we see that like the diff between the baseline and with Tetragon regarding CPU usage is just 0.21%. Like if you compare that to traditional security solutions that do similar monitoring or like runtime security, but they are not that heavily relying on eBPF, we see that they can take up to like 3.6 something percent CPU overhead compared to baseline. And with that, let's quickly dive into some EKS specifics for Cilium, because on EKS you have multiple options of how to deploy Cilium. Like first of all, there's the so-called AWS ENI mode, which is also usually our recommendation, and it basically fully replaces the like default CNI from EKS, which is the AWS VPC CNI. And like with this mode, Cilium directly integrates into the VPC IPAM and fetches the IPs from there. Like another alternative is running like your cluster without any CNI, basically using, for example, EKS CTL, disabling all the network specific plugins like the VPC CNI itself and kubeproxy, deploy Cilium on top of it, and then you are running overlay modes, for example, based on VXLAN or Geneve, which then allows you to kind of, be a bit more flexible and a bit more independent of the underlay from the VPC. Last but not least, there's also this more kind of sometimes seen legacy mode where we do CNI chaining with the AWS VPC CNI, and there it's the VPC CNI that still takes care about port connectivity, about the IP address management and assignment and so on. But we have Cilium like next by running and do the actual, for example, network policy enforcement or load balancing or like ingress and encryption, third-party encryption, and so on. So just one slide for the first deployment method, because it's also our recommended way of deploying Cilium on it. That's the ENI mode. And here we see that once you deploy it with that, we see that the Cilium operator here on the right-hand side of the slide is communicating to the VPC IPAM, fetching new IPs, like caching them within this so-called Cilium node custom resource definition. And from there, it's available for all the agents, or like in particular here for this specific agent running on the node to where the Cilium node CRD belongs to. And from there, you can take the IPs. Once an IP is taken from there, assigned to a pod, it's updated as like a used IP address. And like, as you may know, depending on the chosen EC2 instance type, you have a limitation with regard to how many ENIs you can attach to this particular ENI EC2 instance. And because of that, we offer a so-called sub-feature, which we call AWS ENI prefix delegation, which allows you to not only assign a single IP address per ENI, but rather /28 ranges, for example, which then allows you to run way more pods on the same type of EC2 instance. Then another pretty handy feature that can also be easily used on EKS is the Cilium egress gateway. And it allows you to configure like a deterministic like source IP from which the basically connection from a pod is leaving the cluster. With that, you could, for example, assign static IPs to a whole namespace or to just a subset of specifically labeled pods. And then whenever such a pod tries to connect to an outside system, we see that it's routed through those so-called Cilium egress gateway nodes. And with that, it's always leaving the cluster with the same source IP, so you have a guarantee on your physical firewall, on your traditional firewall, and can still do the traditional access list-based filtering over there, for example, to reach a kind of legacy system like a legacy external database.
A big question to that.
Yeah, sure.
Is that also an EKS pod that is running, or is that an EC2 instance?
You mean the egress gateway node?
Yes.
That's the actual node. That's the actual Kubernetes node. You could taint it, like, and then only have specific workloads, for example, infrastructure workloads running on it. Or there's an alternative, which is right here shown on the next slide. You could also configure, well, it's this slide and the next one, but like here, it probably gets a bit more clear because we have the list of egress groups where we have multiple nodes, for example, one node per availability zone to provide like HA. And here in this example, we see that whenever this pod there, this puller pod, tries to connect to this external echo service on an external EC2 instance, it always needs to leave through one of those 4 nodes. So it always gets mapped to one of those specific IPs. Now you can have multiple IPs per egress gateway node. You can also have multiple interfaces per egress node. That depends a bit on your overall architecture. But what's also possible is this third bullet point here, which essentially allows you to integrate Cilium's BGP control plane with the VPC route server. And then you can peer BGP and use a dynamic so-called egress IPAM IP pool from where the IPs, like the static egress IPs, are taken. And whenever there's one taken, it will be announced to this VPC specific route server, which were just announced GA, by the way, a few weeks ago. And it's then announced to this external BGP and therefore routable in the underlay in the VPC. So with that solution, you do not rely on actual nodes anymore because you can take any node and the egress IP is then just dynamically assigned to this node, which is also selected by the policy here we see on the right-hand side. And yeah, let's also briefly talk about the 2 other bullet points from this scaling Cilium slide. Like we have quite a lot of especially huge customers, especially from the States, that are leveraging EKS together with Cilium. And we've seen like multiple scenarios in the past, like over the few years, where, for example, depending on how you configure Cilium and so on, you can put quite pressure on your EKS API server. So depending on the cluster size, it might make sense to, for example, use the so-called Cilium endpoint slice feature that allows you to dramatically reduce the load on the Kube API server. So whenever you have larger cluster, for example, above 1,000 nodes, or let's say above 20,000 pods, that's probably the latest time when you should have a look at those Cilium endpoint slices to decrease the load on your control plane. Then another feature which is often requested by EKS customer is like, hey, look, Cilium is cool, but like we would also kind of like to reduce our inter-availability zone communication. In the end, also to have like a bit lower latency and so on. So, for example, if you configure your Kubernetes services like you see here on the right-hand side, there you can configure a so-called traffic distribution. And for example, if it's set to prefer close, it always tries to select the backend of the service, which is in the same availability zone, if available. If it's not available, obviously, it still switches to the other backend for fault tolerance reasons. There are a few other like potentially interesting blog posts, some from Isovalent, and I found another pretty interesting one from AWS, where they show how to deploy Cilium networking on top of Amazon EKS hybrid nodes, where you run the nodes in your, for example, your own data center or just any other data center. And yeah, with that, there are plenty of resources available regarding Cilium. We have a huge Cilium OSS community. Whenever you try to run Cilium, run into an issue, feel free to join our open source Slack channel. There we have a community of about 20,000-30,000 people, and they are, like, the vast majority of them are absolutely willing to help. And yeah, with that, I would also like to highlight that we are a proud sponsor of Cloud Native Zurich. So whenever you plan to visit this conference upcoming this summer, please come by our booth and let's have a chat. And with that, let's start with the hands-on lab. So the hands-on lab will be based or will be available through Instruct, which is our lab platform. Well, not our platform, but we use this SaaS. And there you have everything in your browser. Each of you will get his own 6-node EKS cluster. So all of you will have an own EKS cluster with 6 nodes. You will be guided through the lab step by step. You will have a look at Cilium, at Egress Gateway, at Hubble, at the Hubble UI, at some Grafana dashboards, at Cilium Egress Gateway, and Tetragon Enterprise, for example. So just visit this link. You will see a small form where you need to enter your first and last name, your email address, and that's it. You're ready to go. I already preheated 40 labs. So the wait time should be reduced to a few seconds. Whenever you signed up, you should get a lab instance assigned right away. Otherwise, it would take, like normally without preheating, it would usually take between like 15 to 20 minutes to spin it up. But yeah, once spinned up, you have full control over this cluster through the web shell. So there's no need to install anything. And if you have any questions, just raise your hand, let me know. And yeah, with that, even though I added the QR code there, I highly recommend opening the page on your laptop because the whole console would otherwise be a bit too small. Yeah, with that, have fun. Let me know if you have questions or issues. And yeah, I will also be around, walk around and assist whenever there's need for that.